So our next speaker today is Dr. Howard Koo, who is Senior Vice President and General Manager of the Silicon Engineering Group at Synopsis. He manages products and solutions that address semiconductor manufacturing technology needs, and that includes TCAL, yield management, mask data preparation, optical design and analysis, photonics designs, lithography solution, and mass patterning. Before joining Synopsis, Dr. Koo served as Avant Executive Operating Officer as well as General Manager of Avant's Mixed Technology Division and Head of the System Product Line. He also held senior management roles at Analog and Mentor Graphics. Dr. Koo received his PhD in Electrical Engineering and Computer Sciences from UC Berkeley and graduated with a BS degree in Electrical Engineering from National Taiwan University. Dr. Koo.
Thank you. Thank you, and good morning. I really want to say the first thing is thank you giving me the opportunity to speak to the lithographers, the experts in this conference. And also want to thank the event organizer to give me such a tough act to follow after Dr. Siegel's speech. And that was a very comprehensive and a very interesting overview of the lithography for the last 50 years. So I can assure you that I will not say anything about lithography in my speech. I certainly would touch on one of the point that Dr. Siegel has made earlier, that cooperation will speed up progress. And we firmly believe that. As one of the themes that I will claim in our 40 minutes, that collaboration and taking another step further, it is important to our industry. So I would try to expand from a broader semiconductor industry perspective, standing on a very little soapbox to say that we needed more collaboration. We need broader and deeper collaboration earlier. And of course, with a disclosure, which is that it's really EDA industry's perspective that we want to have the EDA industry collaborating earlier with the industry segments more for the semiconductor industry. So here I was going to go into our presentation. Again, you can see that we really are focused on the collaboration from the EDA perspective. From the beginning, I want to give you a taste of what is Synopsis. I'm sure that there are some of our customers are sitting in the audience today, so you know what we do. It's probably a good number of the people here don't really know what EDA industry is really about, and probably not that much about Synopsis. So we'll give you a small number of statistics on the left-hand side, and then give you a picture. Really, Synopsis and EDA is a software company, and we're also very much a technology-focused company. To the right-hand side, I'll give you a picture of what Synopsis is about. What we call the butterfly diagram in the middle of this chart, that graphics, has been the vision that Synopsis has been building for the last 25 and a half years. We really are looking at, from the inception of an end product in mind, and all the way to the physical manufacturing of the end products to satisfy our customers' needs. And in the process, we categorize products and technology categories into system, into verification, into IP implementation, and to manufacturing. We also taken another angle of two axes. One is from the axis of functional, and the other axis from the physics axis. As the recent trend indicates, we're just going to highlight some of what we think are the important trend in our world, seeing on the functional axis that we're seeing the debugging capability, just like what in the manufacturing, we're trying to find the yield limiters, we're trying to find hotspots. Debugging in the system level and the software level is becoming more important and also becoming more available and productive. The IP, the intellectual property, here we really meant silicon IP and verification IP. The reuse is also a very critical trend that has been increasing. On top of that, then, to deliver a chip, a semiconductor chip, and by now you must know that a lot of software had to be built on top of it in order for the product to be satisfactory to the end users. And so we have to put the design of the hardware and software together in a system design perspective. Then we'll turn around to the physical axis. The core of EDA has always been in the simulation and also in the placement route and extraction. That because of the shrinking of geometry, the physical part of the implementation becoming more and more critical. And it's becoming a very critical part of the EDA industry. So placement route and extraction is almost a very important core of a chip design. And of course, associated with that, we're also paying attention to how that translates into mass creation aspects, where the computational lithography participates. And also, we also worry about getting the yield ramp in order to build the end product. And finally, we at Synopsis, and also as many in the EDA industry, we collaborate with leading foundries, fabless, and IDMs. And that's where the angle that we're seeing the effect of our history of collaborating with all these different entities. And I think this goes to why we're looking at the collaboration as an important part of going forward for our industry, and why that we believe that we should take a small step further. What we have been seeing is that although that there are different cases, like the collaboration that Dr. Siegel mentioned, that has taken place, that people are sharing, there are alliances being built, trying to have multiple parties collaborating. But with EDA industry's participation, the collaboration has mostly been one-to-one. Okay? And we're just showing you a small sample of the collaboration that we have done and we have published to the public. We also have seen claims of collaborations, a proposal of collaborations between different functional part of the industries. Some of those being proposed by esteemed colleagues in this audience and in this conference. And the most knowledgeable one has been, maybe we redacted the terms a little bit, is between the process development to the production side, which include lithography, and the design side. Okay. And I think there are also companies out there, entities out there have been practicing a tight optimization in a synchronized fashion between these pieces. From what we have seen, we're making a small expansion of the concept. We believe that there are multiple pieces have been participating from the different parts of the semiconductor industry. And so we have made an attempt to re-describe the system, and you certainly can debate some of the terms and all the system components being added in there. But we added a research consortium to deal with pre-competitive research. We added, of course, the semiconductor equipment industry into the picture. We believe software needs to be part of it. And what we're really familiar with in the EDA industries, we think the silicon IP is also a very critical part of it. Of course, the design side. And certainly, just to make sure that you see where we're coming from, is that we're coming from the EDA angle. So the data, the examples, the logic that we're going to put forth in front of you in the future, the next set of slides are really from that angle. So the first thing we're going to try to state is that, and it's probably a known thing to you, is that the complexity is growing tremendously. And we think it's a systemic complexity, and because there are many coupling effects between them. And I'm sure some of these are familiar to you, but some of them probably from the EDA industry is a little bit different for you. First of all, I want to come from the angle of the end products. From the end products, it's probably it's reasonably safe to say that the data access has been a core of the convergence that enabled many industries that can leverage what semiconductor industry can provide. And this is, again, following Dr. Siegel's response earlier to where you would encourage students to take on the lithography and where the semiconductor industry is going to have a future into different industries. And our view is that the convergence of the different industry on top of the ability of data access, I think the semiconductor industry as a whole has very, very many possibilities for us to apply our expertise and find different growth in the different industry segments. It's all a matter of just within our imagination and our efforts. And of course, this convergence also creates a pressure, which is time to market. There are some of the industry, I'm sure some of you are very much aware of, such as the handset. And the time to market is so short that I'm seeing the pressure with the partners that we're working with. I'm sure many of you are running into that. And of course, the other part, as part of this SPIE Advanced Lithography Conference, and I can't say nothing about lithography. So this is the slide I'm contributing to talk about lithography. And this is a very generic one. I'm sure all of you will probably agree with that, is that the lithography's progress with staying the 193 nanometer scanners, whereas the feature size has now been working at 2220, or you call it 1614, whatever you call it, or 10 nanometer. There is a big gap. And that's another reason why that we have this complexity. And as part of this computational lithography coming into existence, why many of you think that are such a productive and important aspects of enabling us trying to bridge that gap. And as a result of that, the Moore's law seems to be continuing so far, and despite all, we have been saying that we're running into a wall. And especially for EDA industry, we're seeing that the logic design are also continuing to grow, not only in terms of the gate counts, but also in terms of the clock frequencies. And coming along with that was faster frequency and cramming more functionalities onto a single chip. Power is a growing problem, and not only dynamic power, but also the leakage power. And I'm sure that was one of the reasons that many of you are aware of why that FinFET or even SOI have been on the map for a variety of manufacturers as dealing with the leakage power. Okay, from EDA industry, then we're seeing also the other aspects. I want to give you at least one of the curve of the complexity is verifying the functionality. That costs also are exploding. Maybe that's not associated with the physics curve that not every one of you are very familiar with. But from what we have been working with, the number of engineers and the time they have to spend to verify a chip at the functional level, that is growing tremendously. And give you that pie chart you see, that the red part is the debugging part. It shouldn't come as a surprise, right? We're trying to get a chip that has, or a product to be limited in its problems. And it's a critical aspect as more and more applications demand better robustness and reliability. But the other part you should also be familiar with is that the IT infrastructure is also exploding. The more the time and effort that's needed to do the verification at the functional level, the IT infrastructure is also growing tremendously. So the cost is also growing non-linearly. So in the end, what it really does is the overall development cost of the chip is growing tremendously. You can see that the software development cost also growing non-linearly as the components, key components to it. So after say we said the GDS2 was made, there is also associated with now the mask creation cost, certainly this is the part associated with OPC. You can see that as the different technology nodes, there are more RETs are demanded and will be already being experimented. And know that some of these techniques, some of them are not really used. The fact that we actually had to go explore that. And I'll tell you, the EDA industry, we're working on computation lithography. We have to work along the way in doing the research and the past finding steps. So the complexity is probably showing even more than we have shown on this slide. And after that, complexity associated with the files also get so much larger. And we're looking at terabytes of size of the files. And associated with that, then the write time on the mask. That is also growing tremendously. So we are seeing many challenges in order to get that down. So, corresponding to what I said earlier, the time to market. Remember, that's not giving us more rooms. The fact is, this is one example that as Synopsis, we work with a lot of the chip designers around the world. We probably have more than 90-95% of the sign-off market. So we know where the design is being done around the world. At a 1640 nanometer process nodes, we already see more than 25 active designs already taking place and working with that. We're certainly not seeing the 100%, but that's a big number. So you can see that the pace is not slowing down. And so therefore, as an overall semiconductor industry, we need to be ready. Okay, with those complexities, I'm sure every part of the industry are doing our best to cope with it. And so what I'm going to give you in the next few slides is from the angle of what is the EDA industry have been trying to do to manage those complexities. And I'm going to use the similar way of going about and giving you that description is from the functional axis, and then we'll go through the physical axis. And we'll focus on the verification, debugging, and the IP, silicon IP on the system side. And I'm not going to go jump into place and route technology skills, but we're going to instead to talk about the tough topic of the day, which is the power. How do we deal with power management and overall, and of what kind of things the EDA industry has been contributing into helping with the yield learning and the yield ramp. For verification, since what we're dealing with is the growing complexity and also dealing with the time and efforts, this is growing tremendously. So one of the easy things to look at is that, well, I'm sure some of you would have to go to your tool supplier, whether it's the semiconductor tool, equipment tool supplier, or the software tool suppliers. Well, make it run faster. And that's what we have done in verification, the functional level. We have increased the simulation time. Not only that, we also made the verification reusable. This is similar to a silicon IP concept. We're able to get the results of sub part of the design after it's verified. We're able to reuse it, called verification IP. And of course, the other part is debugging. Right? So this is correspond to why we call it the electronic design automation industry for EDA. So automating the debugging is also one thing that we are helping to contribute to cutting down the time and effort that's needed to do the verification. So you can see that for those steps, that's one of the things we have been doing and trying to reduce the time and the effort that's required. Silicon IP, this may not be a very prevalent concept for this audience, so I will give you kind of an example. If you look at a chip, and those purple blocks are reusable silicon IPs. And basically that we have a design, we lay them out, we tested the specs, that we make sure that will fit into a standard surroundings, so to speak. Right? You can see that the percentage of that as a chip is, in this particular case, is very high. As a matter of practice, it has also has become very high. And that's the part of our help to make it easier to design something that is 10, 20 million, or 100 million gates out there. You can see there are a lot of functions on top of that. There will be interfaces such as USB, PCIe, SATA, HDMI, memory interfaces, or even subsystems. And that's one of the next step we're doing is that if you have a sub-block that is composed of many silicon IPs, you can have even a higher level of functionality that it could perform. So we call it subsystems. And so if you look at the lower right-hand corner, which is an audio video subsystem. Now we'll come to the system design level. Now, this really is focused on how do we get the overall design time down. And this, if you look at the upper right-hand corner, the traditional way of doing it, which I think, put it simply, is that when you have a chip finished and ready to test, then you can load your software on top running it. It's kind of a waterfall model, right? That's the traditional flow. What we're trying to do is that make it into a model, whether it's a simulation model, then it's a virtual prototyping. And if it, at the lower right-hand corner, give you the picture of the time you're able to save. We are able to test the software before the chip is finishing its design, before it was laid out, before it has a mask made, before it has a wafer coming back. So that's the time that we are working, and we have produced capabilities today to enable the users to do system design to cut down that software development time. Now we'll come to power management. Now, this is something, as I said before, it was critical in terms of building the next generation chips, especially in the mobile world. Right? Not only that, there are aspects of the process that is targeted to improve that, which I'm not going to speak to in this section. What I will talk about more of, there are design techniques that was conjured, that was imagined. Its purpose is trying to reduce the power consumption at the design, the logic level. And for example, there are many things being used today. There is a clock gating, power gating, multiple VDD, and level shifters. And those are design techniques that have been deployed. With those design techniques targeted and the design I want to use, what it comes down to is that the full ecosystem on the silicon IP side, the standard cell library, the memories, then it needs to be built with those physical libraries, have those design techniques included in them, or else you wouldn't really be able to take advantage of that power minimization techniques. Further, the EDA tools that needed to go and support that, and that's why we have to put things into the placement route tools, into the logic synthesis, into verification tools, that all are in sync with what the assumptions of these design techniques would do, and help to validate whether those design techniques indeed provide the necessary power savings before you commit it to silicon. And finally, in order to do that, there are some aspects of the process that needs to be modified. For example, if you want to have multiple VTH, then you need to go, and from what I understand, there are some approach really is to go and build more multiple implant layers that also have associated with that, because of the cost consideration, there are adjustments to how those implant layers are built. And as an example, for example, then in the past, you may not need to run OPC on them now because of all the changes, then you need to run OPC on them. So that gives you a picture of what the power reduction techniques targeted from the design side was impacting on the EDA industry, and to some degree back into the process side. Also on the EDA industry, as our contribution to the yield ramps phase, is something that many of you probably have heard or being spoken about on pattern matching. And this is just one angle that we're describing, that what happens is that what we're seeing is the yield learning phase. And we applied yield analysis to do correlations, to do statistics, to really validate which are real yield limiters. With those yield limiters, and then we use primarily in the design rule checker phase, do pattern captures, and we add them to database. Most of the time are encrypted because those are really process-specific yield limiters. And those databases then will be used in the next phase where people want to start a design, and then the same design rule checkers could go into those pattern database and do pattern matching to see if there are constructs that maps into those known yield limiters. And then you say, well, don't do that, and make sure that the design will be compliant. And so you go and repair that in the place and route stage. And so that's give you kind of the sense that how some of our EDA industry's involvement in one aspect of the yield ramp. So that was just some samples. Obviously, we could be comprehensively listing all of them. On this slide, we'll give you a picture. There's, in every aspect, there are more and more techniques that we are developing, we're researching, we're collaborating with our partners to build them. So for example, we're building from the debug side, unified debug environment. We're building more of a complete audio IP subsystems, working with ARM to build their virtual prototyping development kit for ARM Big Little architecture. We're making sure that the verification is in design such that you don't have to go do a time-consuming sign-off verification at the end. That you could do that much earlier, can change the place and route incrementally. We're doing the distributed processing, the pipelining, the mask creation stage, and of course the hotspot correlation we just talked about. So we talked about complexity. We talked about the what EDA industry has been trying to work on our own to manage those complexities. When I mean by on our own is basically we're getting requirements, we're producing outputs, and someone will validate that. But we think, and as it is our premise from the beginning for this session, is to say we believe that going forward we need broader and earlier collaborations. I will give you a small number of examples for that. Well, first of all, multiple patterning. Don't worry, I'm not going to go into the details. I'm not that strong a lithography background, so we're going to just focus on the EDA and the flow side. Well, just assuming that the multiple patterning is needed, right? Whether that's LE double patterning, you're talking about SADP, or you're talking about triple patterning. What we have seen is that you're certainly going to have to work with it and make it happen, and you have the alignment tolerances you're going to have to deal with. That. As a part of that, we're seeing different design rules are unique coming out of different fabs. Okay? And to do that, we're seeing that for the EDA tools, we need to make sure that we're producing tools that can ensure that they are compliant with those rules, and that could provide the coloring such that the decomposition into 2 masks or more are going to be okay. And not only that, we're seeing that there are timing issues associated with that people are concerned with. And so we have to go make sure that was okay. And so in the place and route needs to be aware of that. The design rule needs to be implemented. And for our extraction to figure out where the RC parasitics, and that needs to take into account. Now, that is onto multiple masks as opposed to a single mask when you extract them. And so there are many new technologies EDA industry has to develop, but it's coming from the needs of the new techniques that is developed for the improvement of the process. And associated with that also are silicon IPs now also need to be compliant with all the different rules and requirements that associate with that. So maybe I've been kind of cursed with this slide, but as a matter of fact, for us, I think in the whole industry, we have been struggling and trying to figure out how exactly to do that for a much longer period of time than we typically will implement the feature. And I think that it's one of the reasons that it triggered our thinking is that we need to have probably a collaboration in a more systemic manner. The next one is FinFET. This certainly is one of the hotter topic in the front of the line these days. And we also see that there needed a lot more systemic innovation among us. Because of the TCAD technology that we have, we see that pretty clearly. We actually started working with research consortiums. You can see that on the middle lower part of the diagram, we've been working with IMAC and looking at different materials that could be used. And even as of this moment, we're still continuing to collaborate with different universities, academias, and some of our partners to figure out what is the right channel materials that would be the best, including 3.5, to deal with this. With that pre-competitive collaboration that we were doing, certainly we'll go into the process development, and there is associated with that was what kind of etch that needs to happen, right? And associated with stress, and that's why you're looking at the geometrical shape, that whether that's tapered and what was the angle, was there any orientation associated with that, and that besides what the process development team is doing, we actually are collaborating with our TCAD teams, and also that we also see the effect of in the computational lithography, then you have a better etch model when you're trying to do the proximity corrections. So therefore, in the EDA industry, in the TCAD side, that we're not only have to deal with stress, we're dealing with different material characteristics, into the mobility equations. We also need to deal with the fact that now you need to worry about the process window. So variability here associated with different materials has tremendous impact. The epi models that need to be in place. For extractions now, we need to deal with 3Ds. Okay? Today, the extraction for parasitics in the EDA world, to satisfy the need of the designers of quicker turnaround time, it has been a 2D extractions. We've been pushed and shoved into doing 2.5D extractions. Not that we don't want to do 3D, it's because it takes too much time. It's way too much time to do it. Well, with FinFET, I think our end user customers are not satisfied that you only have 2.5D. So you gotta have 3D simulations with millions of match points, yet you still have to run as fast as you were. Maybe 2 hours, 8 hours, you gotta finish that. So we also have a lot of things we gotta deal with in the extraction. So in SPICE, we have to go build new models with SPIE models. And we have to go and put in more physical verifications. And there are new constructs that we have learned in the silicon IP need to be put in place in order to enable the FinFETs. So you can see that now we have even broader involvement in the EDA industry into different corners of the semiconductor industry in order to service and support the FinFET technology. And lastly is on URAMs. Maybe 10, 15, 20 years ago, my naive perception of yields, well, those are really the things going to be done in the back ends, right? So I'm not really worried about it. Whereas more and more we're involved, we feel like that, well, actually we have to be involved in many aspects. Well, that's because of there are contributors from many aspects into the defects. If you look at the middle lower diagram, you can see that the yield limiters are coming from the defect-based yield loss, but also litho-based yield loss. There are also design-based yield loss. And one of our product and the yield analysis has proven that we need to have a comprehensive understanding and capturing, and also synchronizing a coherent semantics among different disciplines in order to have all these issues related. So as an example, on the design side, you have the design for test. You got to understand the timing information. You got to know the design rules. Then you go do hotspot identification. You do yield analysis based on designs. But then you do, of course, in the fab, you have wafer-based inspection or mask-based inspection. You have defect management. You have the failure analysis labs you have to deal with. And you have to sort the wafers. And there are many things have to be put together. And the semantics needs to be correlated. And there needs to be good understanding how do you do analysis of that. And in the shortest amount of time. So we also see that the yield ramp from our angle will benefit from very systemic coordinations. So I'll give you the picture of the complexity and the things that we've been dealing with. And we're trying to reduce the impact of complexity. We're showing the examples, what we have been working with from multiple angles of the collaboration. So that comes down to the end, really what we are standing our little soapbox and saying that we as an industry need systemic collaborations, and we need them early and broader. Thank you. Sure. Do you need me for?
So we have time. We have time for a few questions.
Thank you.
Hi, this is Chris Mack. You illustrated exponential growth in complexity and cost of design over time. Do you really believe that mere evolution in EDA tools is going to be enough to keep up with that exponential growth in complexity? Or is some revolution in tools or methodologies for design required? And if so, where might these revolutions come from?
Well, first of all, I think that my theme was that it needs to be a collaboration. So I don't think that we, EDA industry alone, can take on addressing the exponential complexity. Because I think that needs to be solved in a more systemic manner. I'm repeating the theme, but I do believe that there are things that we could perhaps, understanding the buffer of relaxations upfront that allow the EDA tools when we do that we're able to accommodate that. So, but in the history that we have found ways to deal with the fact, for example, when SPIE started, that the speed of the SPIE can only simulate maybe 20, 30, 50 transistors. Today, we can have fast SPIE simulation that dealing with the full chip simulation. And with verification and functional area was gate level or RTL based. So I think there is a solution of using different skills in a combination in a systematic way to deal with that. But we need to understand it and work that together. And that's how I see how we were able to do it in industry. But that takes a long time. So that's the reason I think today, if you want to do that, just like we're doing the hardware, software prototyping, we got to do it earlier so we can figure out a way to deal with that.
Thank you for your talk, Howard. That's Ken Reigler. What do you think, you said you have 25, 16, and 14 nanometer designs that are percolating. What will be the cost, design cost of an SoC at 14 nanometer? Right now, I really couldn't tell you the cost of those designs. I do know that one of the key reasons that we're seeing that is they are seeing a better cost equation compared to the current 20 nanometer designs. So I do see customers speaking that cost equation versus the benefits they get, they are anticipating a better trade-off than at a 20 nanometer. But overall, I think we have seen numbers that on the overall chip developments in certainly more than $100 million for a project.
Chi-Ming Yuan from Freescale. You mentioned to develop the full system flow for multi-patterning, it took Synopsis a little longer than usual. What do you think? Do you think the whole flow is ready for production at 20 or 14, or do you still think there are still some weak spot during your flow? Or not your flow, but just the industry in general?
Yeah, I think that what we've been working on today is certainly ready for production. But the reason that we have been working on for a long time is that I think most of you understand is that there is a need to go validate what the things that we have provided on wafers to see that it's correct. And until the process side is stabilized, that we're going to be working and iterating together with you. The other part is that industry has not really settled on, in the early phase, on where the decomposition is placed at. Who's going to do the decomposition? And I think it was migrating, and so because we started early, so we're evolving along the way. So in terms of the real implementation of the technology wasn't that long, but the pathfinding is a lot longer.
Okay. So John Peterson from Periodic Structures. What about the metrology, to pull all this integration in, to tie in the EDA with the fab and the process? What do you see for the metrology that you need to make it work best for the EDA community?
You're absolutely right. We actually work with the metrology industry also. We actually are building things that can automatically generate certain test structures. We're working with some of the metrology equipments today. But that has not been one of the key area that has tremendous impact that we have seen in the early pathfinding phase. And that was the reason I didn't list it in there.
Hi, Howard. This is Kafai Light from IBM. I'm just interested because design cost is skyrocketing, but manufacturing cost also skyrocket. So I don't know if you have any ideas, or you work with a lot of customers, see that what is actually, which cost is larger? So actually, we justify should we go to more regular, design, and that you need to invest a lot on it, and then or you keep the design and people have to work with very complicated manufacturing technology. So you have any comments on this?
Well, I think that the manufacturing cost really translates to in the end, is the wafer cost for the chip designers, right? And the matter of fact is that the manufacturer who are able to go into this newer nodes, even the equipment industry, are shrinking in terms of number of players, right? The same thing is going to happen to the designers, the fabless houses, or whether that's the IDMs. The people who have the ability to do this $100 million or more projects are not going to be too many out there. On the other hand, those who are willing to go there is because they have huge profit to gain, right? And certainly associated with the tremendous time pressure. But they have huge profits because they have huge volumes. But those are the ones going to go that. But when I say semiconductor industry can have many other angles, there are many of my friends are staying back in the older technology, but they're trying to find different ways of using and redeploy the capabilities of the fabs and their design techniques. And so I think there are plenty of opportunities. It's just left to our imagination.
Thank you.
I actually have a question.
Okay.
Is this working? So my question is, how do you see the adoption of the EUV in terms of design rule and the layout changes and all these verification and the hotspots when you spend so much time today and in the last few years to adapt this to the multiple patterning, let's say, architecture. And now we are bringing back a single exposure option. So will this be disruption, or it will be a smooth adoption from your point of view?
Sure. Thank you. I think that from our perspective, we will definitely welcome the EUV going to production. We see that probably a way to extend the life of the semiconductor shrinking trend further. Right? So we have been working with EUV technology in our computational lithography aspects for a while. And so we have been working with some partners of laying out path of delivering that. So there are certainly challenges, but we're not necessarily seeing its impact going back to the design phase of the EDA as much as the multiple patterning does.
Okay. Let's thanks Dr. Ku again
Right,
for his very interesting presentation.